Hello everyone. So far we have discussed in the previous videos how to calculate the capacitance of parallel plate capacitor and spherical capacitor. So today we are going to discuss how the force acts on two plates of a parallel plate capacitor, or simply, since in a parallel plate capacitor the plates are charged, so definitely they will exert force on each other and we have to calculate that force. So let us start. Let us assume that it is a negatively charged plate. This contains a charge minus of Q. So we know that if we have a negatively charged plate, then the electric field outside this plate is given by sigma by 2 epsilon naught. So let us this point, so here the field will be E equals sigma by twice of epsilon naught, and if you will see about the direction, then it will be towards the plate since the charge is negative, and the field lines are always normal to the conducting surface, so the field lines are normal. It means this negatively charged plate is producing an electric field around it, and its magnitude is sigma by 2 epsilon. Now, to make a capacitor, we know that we need two plates with the equal and opposite charges. So, if I just wanted to manufacture a parallel plate capacitor, I will place a plate that is having plus Q charge on it. And as you can see that now the plate is here, the charge is same but the polarity is opposite, and this will form a parallel plate capacitor. So my second plate is placed in the electric field of the first plate, and the field is directed towards right. So let us take this the direction of electric field. So we know that if a charge is placed in an electric field of other charge, this charge will definitely experience a force. Let me take the area of each plate as A, and we have also discussed in the previous class that if the sheets are large in shape, so we can ignore the fringing of electric field at the edges like this, and the field is almost uniform between the plates. So for this plate containing positive charge, it is placed in an electric field of sigma by 2 epsilon naught produced by this negative charge plate. So my electric field is sigma by 2 epsilon naught. So force on plate, say this plate is 1 and this plate is 2, plate 1 can easily be calculated by applying the formula force equals charge multiplied by field. So if I will put the value here, I will get Q times sigma by twice of epsilon naught, and F1 as, since you know that sigma is charge divided by area, so on simplifying we will get Q square by twice a epsilon naught, and this force is in the same direction of electric field. It means force and electric field both are parallel to each other. So this is the amount of force that will act on this second plate. Now let us do another activity. If I will place a positively charged plate first, then it will also produce a same amount of electric field, and for positive plate you know that the field lines are away from the charge and normal to the plate. So if I will find out the electric field of first plate, then the electric field of first plate will also be sigma by 2 epsilon naught, and this field will exert a force on this negatively charged plate. So if I need to find out the force on second plate due to the charge on the first plate, it will be charged, and now the charge is minus q on the second plate, and the field is sigma by 2 epsilon naught. So which on simplifying gives minus q, density is q by a. So this force comes like q square by twice a epsilon naught, and this minus sign indicates that the direction of force is not same as the direction of electric field. In fact, the direction of force and electric field both are opposite to each other. It means that this plate will exert a force in opposite direction of field, that is E, and according to this, force is in the direction because force is positive. So this force F1 is in the direction of electric. So this is the way you can find out the force between the plates of parallel plate capacitor, and the force direction can be easily calculated if you will place the charge with its proper sign. Now this is the case where I am just assuming that my charges on the plate is constant, and that is only applicable when there is no battery connected to this parallel plate capacitor. So what will happen if I will connect a battery? So let us see this. Consider it is a parallel plate capacitor. The separation between the plates is T. Charge on each plate is Q, plus Q and minus Q, and I will connect my capacitor with the help of a battery. Now we know that a battery always maintains a constant potential difference between its ends. So as the battery is connected, so now the charge cannot be taken as a constant, but we can take the potential difference between the plates as a constant quantity. So if battery is connected, then the charge will not be constant. So we cannot calculate the force by this formula. So we need to convert my formula of force in terms of a constant quantity, and that constant quantity is potential. So for that, if I am talking about this force F1, say as in this diagram, so this F1 is Q square by twice a epsilon naught, and we know that Q is CV. This is from the definition of capacitance, since the potential difference is V and the charge on each plate is Q. So I can put it here. This is going to be C square V square by twice a epsilon naught. Again, we know that the capacitance of a parallel plate capacitor is A epsilon naught by D. So if I will put this value here, on solving we will get F1 as epsilon naught A V square by twice of D square, and as you can see it clearly that force is proportional to area, proportional to the square of potential difference, and a very important thing, that force is inversely proportional to the distance of the square. Let me write it here like this, and it is giving the idea of the Coulomb. That if you will increase the separation between the plates of parallel plate capacitor, the force will definitely decrease in that case, right?